Let's move on to spherical mirrors. And how do we make spherical mirrors? What we do is, we first take a sphere, and in that sphere, we can cut that sphere to form spherical mirrors. And how do we achieve that? Let's understand. If I have a sphere, what you can do is cut it, or rather insert a plane and cut across a plane along this line, or rather this plane. What happens is, this portion of the sphere comes out of the sphere, and if you polish this end, this surface, this face of the cutout portion, this becomes non-reflecting. This becomes a reflecting nature. This essentially is a hollow sphere. So this becomes non-reflecting and this becomes reflecting. So this kind of a mirror is known as concave mirror based on its geometry. I can also do something else. I can also polish, or rather shade, the inside of it. So let's do it in the other side. The same thing. I cut out the part of a sphere and polish a silver this face or this area. Now this becomes reflecting and the inside becomes of a non-reflecting nature. So this kind of a mirror is your convex mirror. So this is your concave mirror in which this side is your reflecting, and this is your convex mirror in which this bulging outside is your reflecting side. And both of them can be made or cut out of a hollow sphere, right? Now let's understand few geometrical properties about concave mirror and convex mirror. Let's say you have a concave mirror. If this is a concave mirror, whenever I say concave mirror, I can safely presume that it must be part of a hollow sphere from which this is cut out. So that hollow sphere must be having a center and a radius of curvature. So even this concave mirror would be having that same center and that same radius of curvature. So let's try to locate that center. So if you connect the center in such a way that this line is passing through the midpoint of your mirror, then this line is known as principal axis. And this length between C and the point where principal axis cuts the mirror is your radius of curvature. And this point is sometimes also known as pole of the concave mirror. If a ray of light is passed along the center of curvature, it would just come back in the same path. That is based on the idea that if ray of light is passing to the center of curvature, it is falling perpendicular to the mirror, or rather it is falling normally. So this is a case of normal incidence. So whenever you have a normal incidence, principle of reversibility comes into picture, and this reflects the light in the backward direction. Similarly, even if your ray of light is passing, let's say, in this direction, in this situation, it is a case of normal incidence, because any line, for that matter, passing the center of curvature would be of a normal incidence nature, which would mean that this line and this line both are normals to the mirror at different points, which means they would retrace their path. Now let's have a different sort of a situation now. Let's say you have parallel rays. If you have parallel ray coming to this mirror, this is your incident ray, this is parallel to the principal axis. Whenever I say parallel, it is parallel to the principal axis. Now, how would reflection happen? Any line passing to the center of curvature is a normal, and it should also meet this point. So this is your normal, which means this angle becomes your angle of incidence, and similarly angle of reflection would also have the same value. This is your angle of reflection. So if I take this as I, even this is also I, right? Now if these two lines are parallel, according to property of parallel lines, if this is I, even this would be I. If these two angles are of the same value, this becomes your isosceles triangle. I can take this out and draw it for you. This is the construction which I'm making. This is the point where this thing is meeting. This is the ray, or rather the normal at this point. This is your I, and this is your I, right? Now, this is from the center of curvature to a point on the surface of the sphere, essentially, because concave mirror is part of a sphere. So this is your R, right? And let's say this is my X, and this is also X, because this is an isosceles triangle. I have to find out this X, right? How would you find this X? By sine rule. This by sine of this. How much is this angle? This is pi minus this plus this, which is 2i. So r upon sine of pi minus 2i is equal to x upon sine I equal to x upon sine I. Now these two sides are same, so it doesn't make any difference if I exclude it or include it. So essentially what you have is a relation between r and x. If you carry this out, what you get is x is equal to r, this goes here, r sine I upon sine of pi minus 2i. Sine of pi minus theta is equal to sine theta. So this becomes sine of 2i. I know that sine 2i can written as twice of sine I into cos I. Just write that thing. This is r sine I upon 2 sine I into cos I. The sine I thing goes away. What you have is simply r by 2 cos I, and this is your x, r by 2 cos I. Now there's a thing over here. The concave mirror, which we generally use in our day-to-day laboratory purposes and practical purposes, have small aperture. You understand there's something called small aperture. When I say small aperture, all the angles which the parallel rays would make, I essentially, would be of very small value, won't be of a large value. If the angles are of a small value, cos I is almost equal to 1, because for I much less, this denotes that angle is very small. I can assume, or rather approximate, cos I equal to 1, which means x becomes r by 2, because cos I is 1, so this x becomes r by 2, which means that all the parallel rays would meet at the midpoint between the center of curvature and pole, and that point is known as the focus of the concave mirror, and distance of focus from the pole is known as the focal length. So F here is the focus or focal point, and the distance of focus from the pole, PF, is known as focal length. And we have found out the magnitude of focal length for a concave mirror of small aperture would be equal to r by 2. Now, if the aperture is not small, it would be this r minus x, because x is from center of curvature. I need PF. So total is r minus x gives you focal length. So if the aperture is not small, then your focal length becomes r minus r by 2 cos I. But you won't be dealing with this. This would never come into your situation. So just forget this. I mean, just take it into account as a mathematical exercise, not as a physics exercise. Now, this we have done for a concave mirror. What happens for a convex mirror? In a convex mirror, situation slightly changes. This is your convex mirror. Again, I can draw a principal axis which contains my center of curvature, and over here the center would be to the right of it. In the concave case, it was on the left side, but naturally you would see that it should be on the right side. So this is your center of curvature C, and this is your pole of the convex mirror. Now this is my reflecting surface, so the ray of light must pass through this direction. It should not be here. Now if I pass a ray of light pointing towards the center of curvature, normal incidence, it will come backwards. So this reversibility, even if you point it in this direction, even then it would just revert back. This is because these two are normal incidence cases. What happens if you have parallel ray? Let's see. If you have parallel ray, let's make a normal. This is a normal. So this is your angle of incidence, which would be equal to this angle, I, r equal to I essentially. Now, if I produce this backwards, because if you look at this ray, the reflected ray, it would never meet the principal axis in real sense. Just recall the thing which we have done for virtual image formation for a plane mirror. So similarly, this would never meet the principal axis. But if I deliberately do geometrical construction and produce it backwards, it appears to come from a point in principal axis. And this point is also known as focus. So what is the situation over here? Parallel ray on a convex mirror diverges and it never intersects the principal axis, but by deliberate geometrical construction, I can make this reflected ray meet the principal axis if I produce them backward. And that point again becomes your focus. And I can find out the location of focus and the PF value, the focal length. How? Again, if this is your eye, this is your eye, this is your eye, which means even this is eye, parallel rays, if these are two parallel lines, these are alternate angles. And if you isolate this triangle once more, I'm isolating the triangle, what you would get is this kind of situation. This is your F, this is your C, this is essentially R, and this, if this is I, this is I, this is pi minus 2I, this is I, this is I. Again a very similar triangle. So this X would also be very similar. It would be equal to R by 2 cos I, and for small I, cos I can be approximated as 1. So again this X can be approximated as R by 2. So focal length again is R by 2. So for both concave mirror and convex mirror, the focal length would be R by 2 because my aperture is small, and if aperture is small, I would be small, so cos I is approximated to 1. But the change here is, for the case of concave mirror, parallel rays would actually meet at the principal axis, so I'll have a real focus. But in the case of convex mirror, I'll have to do geometrical construction deliberately to make this reflected ray meet the principal axis, and that would be a virtual focus.